Decomposition reactions, as stated before, are fairly easy to identify. The reason why is because you're only going to have one reactant. That one reactant is going to break apart into two or possibly more elements or compounds. An example of this is going to be ammonium hydroxide. Ammonium hydroxide, when it's heated up a little bit, will produce ammonia gas and water. Hydrogen sulfite, otherwise known as sulfurous acid, if it's heated up a little bit, will produce water and sulfur dioxide gas. H2O2 is hydrogen peroxide, a common compound found in medicine cabinets used as a disinfectant. When it's heated up, it's going to produce water and oxygen gas. And this is an extreme example of a decomposition reaction. This is the compound trinitrotoluene, also known as TNT. It's used in dynamite. And when that reaction decomposes, it produces nitrogen gas, water, carbon dioxide, and carbon. All of these are examples of decomposition reactions. Again, decomposition reactions can't be classified only as metathesis or redox. You'll see at the first two reactions that I gave you, all of the oxidation states remain the same. There are no changes, so it's a metathesis reaction. On the second two reactions, we do have changes in the oxidation states, and for that reason, those two are classified as redox reactions. Now, decomposition reactions are somewhat difficult to memorize, all of them, so you're going to be required to memorize how to predict a specific set of decomposition reactions. Binary compounds. In binary compounds, you basically have two elements. Element A and B combined, they are simply going to break apart into A and B separate from each other. This is the reverse of the synthesis reactions that you have to be able to predict. So sodium chloride is going to decompose into sodium and chlorine. Notice that we have included the subscript 2 on the chlorine because chlorine is one of those diatomic molecules. That's how it exists naturally, and so that's what its formula has to be. And then we've balanced the reaction. Another example would be magnesium nitride. If magnesium nitride is decomposed, it is going to form magnesium and nitrogen. In this case, the nitrogen has a subscript 2 on the reactant side because it has to balance the charges of magnesium. On the product side, it's still a subscript 2, not because it was a 2 on the reactant side, but because nitrogen is a diatomic molecule, and that's how it exists naturally. Our last reaction example is potassium nitride. If we decompose that, we're going to break it apart into potassium and nitrogen gas, and there's our balanced reaction. Decomposition of carbonates. Carbonates are compounds that have the polyatomic ion carbonate in them. The general format is that you're going to have a metal, represented by the letter M, carbonate, and it's going to decompose when this reaction takes place into a metal oxide and carbon dioxide gas. So let's look at a couple of examples. We have sodium carbonate. When this reaction takes place, you're going to end with sodium oxide, the metal oxide, and carbon dioxide gas. In our next example, we have calcium carbonate. Calcium carbonate, when it decomposes, is going to produce calcium oxide and carbon dioxide. Notice the pattern. We have a metal carbonate producing metal oxide and carbon dioxide gas. Our third example, we have aluminum carbonate. A little more complex in writing out and balancing it, but as long as you're balancing the compounds formulas properly, you're not going to run into a problem. We see aluminum oxide, or metal oxide, and carbon dioxide gas. Hydroxides. Hydroxides, any kind of metal with a hydroxide polyatomic ion, they're going to produce metal oxides and water. Our first example, sodium hydroxide. If sodium hydroxide is decomposed, it's going to decompose into sodium oxide and water. Calcium hydroxide will decompose into calcium oxide and water. Aluminum hydroxide will decompose into aluminum oxide and water. Again, in all of these, we are predicting the products, we're balancing the charges of the formulas on the product side using what we know to be the oxidation states, and then balancing the reaction to make sure that you have equal elements on both sides. Chlorates. Decomposition of chlorates. We have a metal chlorate is going to decompose into metal chloride and oxygen gas. Our first example, sodium chlorate. And sodium chlorate is going to decompose into sodium chloride and oxygen gas. Calcium chlorate will decompose into calcium chloride and oxygen gas. Aluminum chlorate will decompose into aluminum chloride and oxygen gas. Again, in each one, we predict the products, putting the elements together the way they should be, making sure the charges are balanced, and then we balance the reaction